Hello everyone and welcome to my channel. This is an educational channel. We look at theories of everything and in particular we do deep dives into some of my favorites that you probably haven't heard of before, and today is our 438th video on the reciprocal system of theory from Mr. Dewey Larson. And Larson calls it the reciprocal system of theory because it is a system. It is a an integrated system. You can there's a reciprocal astronomy, a reciprocal chemistry, a reciprocal economics, a reciprocal physics, and any other subject that you could try to apply it to. If you can figure out how to apply it, you will get results. So it is an integrated system of, kind of figuring things out, figuring out how things work. And if you pay attention to how Larson does it, then you can kind of figure out how to do it in your own field. Whether you want to do the reciprocal system of underwater basket weaving or the reciprocal system. For me, I'd like to figure out the reciprocal system of history, or the reciprocal system of endurance training, or reciprocal system of nutrition. These are all within the ken of the reciprocal system once you learn how to use it. The basic now it's also called the reciprocal system, and it is also called the universe of motion. So Larson tried to build his universe out of motion. In 1959, he proposed his two fundamental postulates about how he believed the universe operated. And, he tried to build his universe not out of matter, not out of energy, but out of motion. And his first postulate does most of the work. The second postulate is mostly kind of axiomatic, but I would say that it is in need of some revisions. But the first postulate states that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Now, in his earliest versions of these, the first postulate actually says the universe is made out of one component, space-time, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. But at a certain point, he changed from space-time to motion. Now, when he talks about motion, he's really talking about a specific kind of motion that is not exactly what you're thinking of. He's referring to what he calls scalar motion. And a scalar motion is a motion that has a magnitude but has no specific direction. You can use a balloon and put a bunch of dots on it with a magic marker. If you blow up the balloon, all of the dots will be moving away from each other. That is a scalar motion because there's no specific direction. Every dot is moving away from every other dot, and there's no specific direction connected to any of it. Everything is moving away from everything else. Everything is moving in every direction. And it's not until you assign a reference point, you arbitrarily decide that one of the dots is motionless, that you start getting some directions involved. And if you contract the balloon and all of the dots will then be moving toward each other. Larson refers to that outward motion as the progression and the inward motion as gravitation. Now, so really he's saying the universe is made out of scalar motion. And scalar motion exists in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Okay, now what he's basically saying is that motion is the relationship between space and time. Now, we do see that in what you would call speed. The car is moving 10 miles per hour, 10 miles of space in 1 hour of time, space over time. And so in this example, motion, speed, is a relationship between space and time, space over time. Larson generalizes this and applies it to all really scientific phenomena. Every scientific phenomena is a motion, and they are all characterized as relationships between space and time, basically fractions with space or time as the numerator and time or space as the denominator. So energy, matter, pressure, temperature, these are all different kinds of motion, and they all can be expressed in space over time or time over space coordinates. And again, time, space, and motion have 3 dimensions. So it could be time to the 3rd power over space to the 3rd power. That turns out to be matter. Time to the 3rd power, or space to the 3rd power over time. That is electrical capacitance. Time over space to the 4th power, in fact, is pressure. Time to the 3rd power over space to the 6th power is density. That's because time to the 3rd power over space to the 3rd power is matter. And matter density is mass per volume. So then you have to multiply another 3 spaces to get volume. Volume is space to the 3rd power. So density is time to the 3rd power over space to the 6th power. And you can also check all your classical equations this way. F equals ma, force equals mass times acceleration. Force, time over space to the 2nd power. Mass, time to the 3rd power over space to the 3rd power. And acceleration, space over time to the 2nd power. It all multiplies out, and that equation is valid as far as the units are concerned. You can do the same with like E equals mc squared, or any other number of equations. There have been a few equations that have been checked out to be wrong, according to the reciprocal system, and those are suspect. Now, you can also see that reciprocal relationship in speed. Like, say the car is going 10 miles per hour, 10 miles of space in 1 hour of time. Let's double the speed. You double the speed, now you can say the car is moving 20 miles per hour. But equivalently, you can also say the car is now moving 10 miles per half hour. So you can either multiply the space, or you can divide the time. That is a reciprocal relationship. So at least as far as speed is concerned, there is a reciprocal relationship between space and time. Larson just generalizes that and applies it to all forms of motion. All forms of really scientific phenomena are forms of motion. Space and time basically have 2 aspects. Their coordinate relations, and then their scalar relations. We went over the scalar outward motion, the progression. The inward motion is gravitation, just like on the surface of an expanding balloon. But now, if you take one of those dots and you arbitrarily decide it's motionless, then you can get directions or vectors, and it actually appears as if there's a force field that is pulling objects toward, like if you're contracting the balloon, that all of the other objects are moving toward that one that you have assigned as motionless. It looks like that one has a kind of a gravitational force connected to it, and everything is drawing all the other dots toward it. That is not real. It's what Larson calls an as-if force, and it only has to do with assigning the reference point. So it's from the reference point, not from the motion itself. And that's where you get what he calls coordinate space and coordinate time. Three dimensions of space, x, y, z coordinates in a still frame. So you get the still frame because you've assigned a reference point. He also calls it the spatial reference system. So you have this spatial reference system of 3 dimensions of space in a still frame, and at the same time you have progressing time or scalar motion in time. Time is always getting later and later and later and later, but in no specific direction. That is a scalar. So that's what we observe in our neighborhood of the universe. We observe coordinate space and clock time. Progressing time, always getting later and later and later in no specific direction. However, if we went into a different sector of the universe, we would witness the inverse of that. We would witness 3 dimensions of space. And this is from the reciprocal postulate. If space and time are reciprocals of each other, then each one of them has the same qualities. Space, we see space as a 3-dimensional thing. Therefore, there is some place in the universe where time has that same quality. So there is a coordinate time, 3 dimensions of time in a still frame, and we observe time to be moving in a scalar manner. And so there is also some place in the universe where space is moving in a scalar manner. Everything is always getting farther and farther and farther apart, like on the surface of an expanding balloon. So in this different environment of the universe, we would have 3 dimensions of time moving through space. Coordinate space and clock, coordinate time and clock space. Now, this comes about through this discrete unit postulate. Space, time, and motion are all quantized, meaning that you have to have a full unit before you have a unit, before you have any quantity at all. You have to have a full unit. The unit of space is approximately 500,000th of an inch. The unit of time is approximately 1/6 quadrillionth of a second. And the unit of motion is when you have 1 unit of space in 1 unit of time. Speed, space over time. Unit speed is 1/1 = 1. So Larson calls that unit speed, and that turns out to be the speed of light. So the speed of light, which is approximately 3 × 10⁸ meters per second, and that is the unit speed of this universe. Really, it's the speed of the empty universe. If you're going to accept a universe of motion, you have to be able to accept motion without anything moving. Motion precedes the thing that's moving. So this motion at unit speed is ever present, omnipresent, and eternal. It's always there, even when there's nothing else in the universe. In fact, it is the source of the universe. Everything that comes about from that original source. Larson calls it the progression of the natural reference system, outward motion at the speed of light in all directions. This is always there, and it always needs to be factored in. So when Larson calls it the natural reference system. So Larson has a natural reference system, and then there's a spatial reference system of coordinate space and clock time, and a temporal reference system of coordinate time and clock space. These stationary reference systems are arbitrary and really are abstract. They involve stopping the universe and taking a snapshot and then measuring that. The natural reference system is the reference system to which the universe actually conforms, and that is the spot from which Larson makes his measurements. And so the discrete unit postulate, 1 unit of space and 1 unit of time, this is the 0 point or the null point or the neutral point. This means that half the universe is moving faster than the speed of light, half is moving slower. The half that's moving faster, Larson calls the cosmic sector. Science knows little or nothing about this. And that is where you have coordinate time and clock space. In the material sector, the sector is moving slower than the speed of light, you have coordinate time, coordinate space, and clock time. Now, within each one of these sectors, the material and the cosmic, there are inside regions of both that are within a unit of space in the material sector and within a unit of time in the cosmic sector. That is because of the discrete unit postulate. If you don't have a full unit of space, then you don't have space. If you don't have space, then you only have time, because the universe is made out of space and time only. And so you got to have one or the other or both. And if you don't have space, then you only have time. Larson calls that the time region. And the time region is the region of interaction of atoms and molecules that interact in less than 1 unit of space. If they interact in less than 1 unit of space, they interact in time. We still see it in space. We see the equivalent of it in space, like the inverse of what's actually happening is happening in time, but we see the inverse of it in space. Larson calls that equivalent space, and you have to basically take the square root, because what's going on is a second power relation, and then you also have to reduce it by what he calls the interregional ratio. That's like what gets lost in the translation from looking into a different sector of the universe or a different region of the universe. He gets into that, and it'll be relevant to some of the study that we do here in the reading. We're reading from this book called Basic Properties of Matter. This is where Larson, he derives a theoretical universe from his postulates through a process of deduction. If this, then that. If this, then that. So if his postulates are correct, he determines a universe, or he derives a universe that looks like this. And then he compares his universe with the measured universe of the scientists. In particular, for this book, he's talking about chemistry. So he arrives at various equations. He derives these equations from the postulates and the chain of deduction. He derives equations for many of the basic properties of matter, such as the melting point and the specific heat and the compressibility, which is what we're talking about today, and the interatomic distance, and many other properties. And so then he compares his theoretical values with the empirical values of the scientists. And in many cases, in almost all cases, in fact, he pretty much just reproduces their tables from theory only. So there, unless he's fudging the numbers in some way, you know he's onto something. Okay, now we're going to take over kind of in the middle of this chapter on compressibility. Now, an atom is formed from the progression. There's several steps that are required. First, the progression turns into a photon, then it turns into 2 photons, then it is rotate, and a photon is an oscillating motion, a wave-like motion. And then the wave-like motion needs to be rotated in 3 dimensions. Again, the universe is 3-dimensional. It has to be rotated in 3 dimensions in order for it to gravitate. And so basically you're rolling back that outward motion of the balloon, and now the outward motion becomes an inward motion. That requires 3 dimensions of rotation. And those 3 dimensions are basically the 3 numbers that Larson uses in his periodic table. And so those are the numbers that kind of get manipulated into these equations for compressibility. Now, compressibility starts in the solid state. and the solid state comes from an equilibrium. What I didn't mention about the time region is that in the time region, the rules reverse, just like the rules reversed when you crossed the speed of light boundary from coordinate space to clock and clock time to coordinate time and clock space. When you go into the time region, the progression is now moving things toward each other, and gravitation is moving things away from each other. Unlike in the outward regions where the progression is moving away outward and gravitation is moving inward. And so in this time region, an equilibrium is established between the constant, ever-present progression, and the variable by the inverse square process, gravitation. And at the place where they're equal is where the interatomic equilibrium is established. And then more pressure brings that closer together. And that is, there is an internal pressure that is supplied by the progression, and then there is an external pressure that can be applied from some outward force, say you pressing against it. And so Larson has to determine the pressure from both of those different factors. Okay, we'll let him go here and see what happens. The nature of the response of the compression factors to the application, the compression factors are basically these three numbers of the periodic table adapted to this particular set of circumstances. Because pressure is two-dimensional and matter is three-dimensional. And so the factors of compression are related to the orientation of the atom, how much of the resistance, because the rotational factors or the gravitational factors resist that compression. And so the nature of the response of the compression factors to the application of pressure has already been explained, and the maximum factors for each group of elements have been identified. So as the pressure increases, more and more of the factors become brought to bear to resist. And so at high pressures, all of the factors of each atom are employed in trying to resist this pressure. However, the magnitude of the base volume, which is the interatomic distance to the third power, also enters into the determination of the internal pressure. And coincidentally, with the increase in these factors, there is a trend toward minimum base volume. In themselves, modifications of the crystal structure play only a small part in the compressibility picture. Applications of sufficient pressure causes a solid to assume one of the crystal forms corresponding to the closest packing of the atoms, either the face-centered cube or the close-packed hexagonal for isometric crystals, and the nearest equivalent structures if the crystals are anisommetric. If some different crystal form exists at zero pressure, the volume decrease due to the change to one of the close-packed forms shows up as a percentage reduction in all subsequent volumes. But the compressibility is not otherwise affected. However, a difference in crystal structure often indicates a difference in the relative orientation of the atomic relations. Any such change in orientation alters the internal pressure and consequently has a significant effect on the compressibility. Compressibility is the rate of compression, and there are two kinds of transitions. The first order transitions are from the crystal structure, or really the interatomic equilibrium, and then the second order transitions are from employing more and more and more of the rotational factors to resist the pressure. So your compressibility curve would normally just be a straight line, but there are inflection points where the crystal structure changes at a certain point, or where the more rotational factors are brought in, that will change the slope of the curve. And so you end up having a curve with a number of different inflection points for your compressibility. Application of pressure tends to favor what may be called regular structures at the expense of those structures that are able to exist only because of special conditions applicable to the particular elements involved. This tendency is evident from the start of the compression process and is responsible for the large number of deviations from the interatomic distance values of that are identified in Chapter 2 in Table 14. For example, the 5 elements from chromium to nickel have a number of different interatomic distances at low pressure and are able to crystallize in alternate forms. In the early stages of compression, however, all of these elements except manganese orient themselves on the basis of the neutral relative rotation 10 and have an internal pressure that reflects the corresponding value of the cube of the interatomic distance, which is 0.603, and that would be in cubic angstroms. At still higher pressures, vanadium shifts to the, or actually, that isn't in angstroms, that's in relative volume. So relative volume would be 1. The volume would be 1 at the 0 pressure. So at this particular pressure, the volume is 0.603. Okay, at still higher pressures, vanadium shifts to the same relative rotation and joins the group. Manganese probably does likewise, but empirical confirmation of this change is still lacking. Thus, the change of variation of the atomic arrangements is greatly reduced by external pressure. One of the collateral effects is that the amount of uncertainty in the identification of the rotation orientation and the resulting base volume is minimized. Most of the elements that change in a lower base volume at the start of compression maintain this new value of the cube of the interatomic distance throughout the remainder of the present range of shockwave experiments. And the shockwave experiments are kind of newfangled at this time when he's writing back in the 80s. That were able to achieve much higher pressures than before, up into the millions of atmospheres, where before the limit was like 100,000. Those that do not make this change in the early stages of compression generally do so at some higher pressure. Only a few keep the same base volume up to the shockwave pressure limit. Still, fewer undergo a second transition to a lower base volume. Thus, the general pattern involves one reduction of the base volume in the pressure range from 0 external pressure up to the limit of the shockwave experiments. This pattern is reflected in the 12 series of measurements that have been selected for comparison with the theoretical values. Out of the 12 elements that are included, only 2, copper and chromium, have the same base volume in the shock wave range as at 0 temperature. 4 continue with the values of the interatomic distance cubed applicable to the early stages of the compression. The values listed in Table 14 and 6 other elements, the other 6, change to a lower base volume somewhere above that 100,000 limit. The minimum base volumes, the corresponding maximum compression factors, and the resulting internal pressures for these elements are shown in Table 19. So we look at table 19, and it looks like he has, just listing these various elements, shows what their rotational factors are, along with their periodic table numbers, which are usually quite similar. And then he also shows the initial pressure and the volume, the relative volume. It doesn't look like he's showing the observed volume. At least I'm not really seeing it. I'm not seeing the observed volume. Let's see what he explains here. Here again, as in the pressure range of the Bridgman experiments from the early 20th century, the theoretical development is not yet far enough advanced to enable specifying the exact locations of the upper sections of the compression curves, nor is it yet clear in all cases just how many of the possible intermediate values of the compression factors are actually utilized as the pressure increases. What we are able to do at the present rather early stage of the development of the theory is to demonstrate that in this extreme high pressure range, as well as at the lower pressures of the preceding tables, the volume varies inversely with the square root of the total pressure, strictly in accordance with the theory. So the volume varies inversely with the square root of the total pressure. That's the total pressure is the internal pressure plus the external pressure. And it's a square root because this is in the time region. And so the measurement is in equivalent space, and that's a second power region. So you have to use a second power you have to adjust for that. Okay. In this connection, it should be noted that the section of each compression curve that is based on the maximum value of the internal pressure is long enough to make the square root pattern clear and distinct. Like before it starts making all kinds of, transitions. Okay, we're going to leave it there for today. Don't get discouraged if you're confused. We're just trying to kind of let this wash over you, and you'll figure it out. It's a detective work. Just get the basic principles. Have a great day.